Hello everybody, my name is Tyler Landway and I'm an undergraduate student at the School of Mechanical and Aerospace Engineering at Oklahoma State University. Today I'm going to be talking about an investigation of airflow around buildings using large eddy simulations for unmanned air systems applications. The contents are as follows. First, we're going to talk about the motivation behind the study, why we used a large eddy simulation, the large eddy simulation setup and results. We're going to talk about machine learning methodology, the machine learning setup and results, and finally the conclusions. The motivation behind this research is that the small unmanned air systems industry is rapidly growing. The Federal Aviation Administration estimates that the UAS industry will triple by size by the year 2025, and many of these applications require operation within an urban canopy. And this is slightly problematic because UAS are highly susceptible to changes in the flow field which is produced by buildings. And to safely integrate these UAS into existing airspace, window-air navigation is essential. So why did we use Large Eddy Simulation, or LES? LES can accurately resolve the unsteady structures in the flow field, and this is critical to our studies because we're going to be studying these structures and applying what we can learn from them to unmanned aerial systems. And so parallelized large eddy simulation, PALM, was used to solve for these flow fields. And 5 different building geometries were simulated in the CFD domain. These geometries represent common building geometries found in urban canopies, and the examples of the buildings that we used can be seen in the figure to the right. The simulation setup was as follows. The overall domain dimensions were 576 meters by 488 meters by 320 meters with an equidistant grid spacing of 1 meter. The building dimensions were 40 by 40 by 49 meters, and the u-velocity was initialized proportional to z to the 1/4. The simulation was initialized using a neutral atmospheric boundary layer, and our domain maintained a blockage ratio of less than 3%. The boundary conditions were cyclic on each side, inflow and outflow, and the inlet and outlet, and a no-slip bottom condition. The simulation was run until a quasi-steady state was reached, and this took about 1 hour. The data was output until a total runtime of 2 hours. Let's talk about the large eddy simulation results. To the right on this plot, you can see the streamlines through the vertical central plane. The buildings create a significant region of circulating flow in the leeward direction, which can be seen by the indicator number 1. And number 2 represents the standing vortex in front of the windward facade. And you can see in this recirculating flow indicated by number 1 that the flow in this region is very complex. And these regions have the highest turbulent intensity, meaning that the flow here is very unstable. These regions represent potential threats for UAS that need to be avoided. This animation is showing the vorticity generated by the bluff building. And it's very interesting to look at because you can see the kind of turbulent structures that are produced by the air flowing around the building. You can see that behind the building and on either side of the building, there is a large amount of vorticity which is being generated. And these areas would be dangerous for UAS to fly in as the flow here would be very unstable. Moving on to the pyramid and gabled cross sections. These are the u-velocity slices through the vertical central plane. And you can see in the gabled cross-section that the velocity disturbances are projected far into both the x direction and the z direction. And this is an indication that the gabled building is doing a very good job of projecting its disturbances very far into the domain. And you can see when compared to the pyramid building that the pyramid building does not project these kinds of disturbances as far into the x or z direction. And this is because the pyramid building has a lower frontal area than the gabled building. And this means that the velocity disturbances which are generated by the pyramid building are not going to be as pronounced as those generated by the gabled building. Moving on to the wedge and the vaulted buildings. These two buildings have a more similar structure in terms of how far the disturbance is projected in the x direction, But you can see that the wedge cross-section has some disturbances that are being projected farther into the z direction as the x direction increases. And this is because of the shape and the geometry of the wedge building. And onto the flat building, you can just see that this kind of acts as a little bit of an average for all the cases. This slide shows the average u velocities at 1h, 2h, and 3h x distance behind the building, respectively. You can see a flow reversal behind each topography as they have negative average velocity below the building height. The pyramidal shape yielded the lowest average velocities, and that's the shape in the blue, while the gabled and wedge shapes yielded the highest average velocities. Those are the shapes in the red and the green, respectively. The large Eddy simulation data generated from the previous simulations was used for training the machine learning model. We used proper orthogonal decomposition along with singular value decomposition to generate model coefficients and projection bases for fluctuation fields. The LSTM network was employed to train on reconstructed data from the proper orthogonal decomposition, completing the ROM LSTM approach. The neural network was trained on 300 snapshots of data and predicted for a further 60 snapshots. The results of these predictions were compared to reconstructive data from true POD models. The model's coefficient evolution is shown for 35 modes, and contours are a small section of the xy plane and the center of the domain. The images in this slide represent an example neural network and the LSTM model. Moving on to machine learning observations. On the right, you can see the relative information threshold plot. We selected 80% of relevant information content for our threshold, and from this, 35 modes were selected. And on the left-hand side, you can see an animation of the true modes number 1 through 8 from 0 snapshots to 300 snapshots. The modal coefficients comparison for modes 1 through 8 can be seen in this animation. The black represents the true modes, while the blue represents the machine learning prediction. The yellow regions of the plot represents the training period. You can see that for each mode, during the training period, the true and the predictions are incredibly close. And then shortly after the training period, the prediction remains very true to the actual value. As the number of snapshots increases, the prediction and the true modes begin to diverge, but they typically follow the same pattern and are in the same order of magnitude. Also, as the mode number increases, the deviation between the true and the predicted values begins to increase. These figures show the u-velocity contours through the center of the domain. On the left, this is reconstructed from the true modes, while the right figure is reconstructed from the ROM LSTM modes. And these show the u-velocity contours from the 300th snapshot to the 360th snapshot. And you can see that the agreement between these two is very close. And they show good agreement in both the structures and the values of the u-velocity. And it will be noted that some of the finer structures are recreated incorrectly, but it does a very good job of matching the overall structures which is created by the LES model. And this is encouraging because this means that we can use machine learning predictions to accurately predict the flow. To conclude, building geometry has a significant impact on the flow field surrounding each structure. The wedged and the gabled roof structures pose the most significant threat to small unmanned air systems as they create a larger region of turbulence. We attempted to demonstrate that the data generated from these simulations could be used for making flow field predictions in a non-intrusive reduced order model LSTM approach. A window-or navigation system is possible with more research into path planning algorithms and onboard prediction methods. Further investigation into the flow field interactions between buildings would be required as this leads to a more realistic result, and it would also lead to a more robust database for wind-aware navigation. We would like to acknowledge the support by the National Science Foundation the High Performance Computing Center at Oklahoma State using the supercomputer, and Cheyenne, provided by NCAR's Computational and Information Systems Laboratory, sponsored by the National Science Foundation. Thank you very much for listening to my presentation.